The phenomenon of the shifting magnetic North Pole is a captivating tale of Earth's magnetic field in flux, a story rooted in geology, physics, and the ever-changing dynamics of our planet's core. This gradual yet measurable movement of the magnetic North Pole, which has fascinated scientists for centuries, offers a glimpse into Earth's deep and dynamic interior. From its implications for navigation to the mysteries of geomagnetic reversals, this phenomenon unfolds like a multifaceted narrative. The magnetic North Pole is not a fixed point but a wandering one, moving across the Arctic over the centuries. This journey, driven by changes in Earth's molten outer core, is a fascinating interplay of heat and rotation. Scientists have tracked the pole's path since it was first discovered in 1831 by James Clark Ross. Over time, its pace has quickened. In the early 20th century, the pole moved at a leisurely pace of around 10 kilometers per year. However, in recent decades, it has accelerated to speeds exceeding 50 kilometers per year, hurtling towards Siberia. This rapid shift has sparked global attention, prompting scientists to refine models of Earth's magnetic field to ensure navigational systems remain accurate. The implications of the shifting magnetic North Pole extend beyond maps and compasses. Modern technology relies heavily on precise magnetic field data. Satellites, GPS systems, and even smartphones depend on accurate magnetic models to function correctly. As the pole moves, these systems must be recalibrated, a task undertaken by organizations like NOAA and the British Geological Survey. The World Magnetic Model, updated every 5 years, has become an indispensable tool for navigation in an era where precision is paramount. Yet, the pole's unpredictable movement has forced scientists to make interim updates, highlighting the urgency of understanding this complex phenomenon. The reasons behind the shifting magnetic North Pole are deeply rooted in Earth's geodynamics. The magnetic field arises from the motion of molten iron and nickel in the outer core, creating a dynamo effect. Changes in this turbulent flow can alter the magnetic field, influencing the position of the poles. At times, these changes lead to geomagnetic reversals, where the north and south magnetic poles switch places. While such reversals are rare on human timescales, occurring every several 100,000 years, the shifting magnetic North Pole offers a window into these larger processes. By studying this movement, scientists gain insights into the inner workings of our planet and its long-term evolution. As fascinating as the magnetic North Pole's journey is, it also underscores the uncertainties inherent in Earth's magnetic behavior. The rapid shift raises questions about the stability of the magnetic field and its potential impact on Earth's biosphere. While the magnetic field shields the planet from harmful solar radiation, changes in its strength or configuration could have consequences for life on Earth. Understanding the shifting pole is not just a matter of scientific curiosity but a crucial step in preparing for potential challenges. By piecing together data from satellites, ground observatories, and ancient rocks, scientists strive to predict the pole's future path and its implications for our world. The shifting magnetic North Pole is a reminder of Earth's dynamic nature. It is a tale of movement, adaptation, and discovery, reflecting the intricate interplay between Earth's core and surface. As the pole continues its journey, humanity's understanding of this phenomenon deepens, offering new perspectives on our planet and its ever-changing environment. This story is far from over, with each new discovery adding another layer to our understanding of the magnetic forces that shape our world. The magnetic North Pole's movement is one of the most striking reminders of Earth's dynamic processes, unfolding beneath our feet in ways we cannot directly observe but profoundly affect our world. For centuries, explorers, scientists, and navigators have relied on the North Pole as a critical point of orientation. Yet, its shifting position reminds us that even the most seemingly stable points on Earth are subject to change, driven by forces deep within our planet's core. Understanding this phenomenon requires delving into the complex interactions of molten iron and nickel, the primary drivers of Earth's magnetic dynamo. The acceleration of the magnetic North Pole's movement in recent decades has created a sense of urgency in the scientific community. Historically, the pole moved at a relatively steady pace, allowing maps and navigation systems to remain reliable for decades. However, with its speed now surpassing 50 kilometers per year, maintaining accurate navigation has become a significant challenge. This movement complicates tasks for global transportation systems, military operations, and even migratory animals that depend on Earth's magnetic field for navigation. The consequences extend to both human-made technologies and the natural world. One of the most intriguing aspects of the shifting magnetic North Pole is its potential connection to geomagnetic anomalies within Earth's core. The fluid outer core, composed of swirling molten metals, generates complex and ever-changing magnetic currents. Scientists speculate that shifts in these currents, possibly caused by fluctuations in temperature or pressure, could explain the pole's erratic behavior. By studying the pole's trajectory, researchers are uncovering clues about the dynamic processes occurring thousands of kilometers below the Earth's surface, offering insights into the broader workings of the geodynamo. While the magnetic North Pole's wandering affects navigation, its implications for satellite technology and communication are equally critical. Satellites rely on models of Earth's magnetic field for positioning and orientation, and these models must be updated to account for the pole's movement. The increasing reliance on satellite-based technologies for everything from weather forecasting to global communication means that accurate modeling of the magnetic field is essential. This dependency highlights how interconnected human activities have become with Earth's natural magnetic dynamics, making their study more crucial than ever. The shifting magnetic North Pole also raises concerns about the strength of Earth's magnetic field. Over the past 200 years, the field has weakened by approximately 10%, a trend that scientists are monitoring closely. A weakened magnetic field can make Earth more vulnerable to solar storms, which have the potential to disrupt electrical grids, satellites, and communication networks. The pole's rapid movement could signal further changes in the field's strength, adding an element of unpredictability to its long-term behavior. Understanding these changes is critical for preparing for potential impacts on global infrastructure. The magnetic North Pole's movement is not a new phenomenon, but modern technology has allowed scientists to track it with unprecedented precision. Satellite missions like the European Space Agency's Swarm have provided detailed data on the magnetic field's behavior, enabling researchers to create more accurate models of its dynamics. This technological advancement represents a significant leap forward in understanding the pole's movement and its broader implications. By combining satellite data with historical observations, scientists are piecing together a more comprehensive picture of Earth's magnetic past, present, and future. The pole's movement has sparked renewed interest in geomagnetic reversals, a phenomenon where Earth's magnetic poles switch places. These reversals are natural events that have occurred numerous times in Earth's history, with the last one taking place around 780,000 years ago. While there is no indication that a reversal is imminent, the rapid movement of the magnetic North Pole has prompted questions about whether such an event might occur in the near future. Studying the pole's behavior could provide valuable insights into the conditions that precede a reversal, helping scientists better understand this enigmatic aspect of Earth's magnetic history. The shifting magnetic North Pole is a stark reminder of the interconnectedness of Earth's systems. From the depths of the outer core to the far reaches of the magnetosphere, the forces driving the pole's movement are part of a complex interplay of geophysical and astronomical processes. These processes not only influence the magnetic field but also play a role in protecting Earth from cosmic radiation and solar winds. The study of the magnetic North Pole is, therefore, not just a study of a single point but an exploration of the forces that sustain life on our planet. As the magnetic North Pole continues its journey towards Siberia, its movement is being closely watched by governments, scientists, and industries around the world. Aviation and maritime industries, in particular, are heavily impacted by changes in the pole's location, as they rely on accurate magnetic data for navigation. The need for constant updates to navigational charts and systems underscores the practical challenges posed by this natural phenomenon. These challenges also highlight the importance of international collaboration in monitoring and adapting to changes in Earth's magnetic field. The story of the magnetic North Pole shifting is both ancient and modern, reflecting the ongoing evolution of Earth and our understanding of it. From the first explorers who used magnetic compasses to today's sophisticated satellite observations, humanity's relationship with the magnetic pole has been a journey of discovery. As we continue to study its movement, we gain not only practical knowledge for navigation and technology but also a deeper appreciation for the dynamic and ever-changing nature of our planet. The shifting magnetic North Pole reminds us that Earth is a living, breathing system, constantly evolving in ways that challenge our understanding and inspire our curiosity.